In this programming example, we will implement a network that solves a regression problem using Tensoflow. Remember that a regression problem means that we are predicting a numerical value instead of predicting a class. We will use the California housing dataset. So for each training example represents a house in California, and there are a number of variables about that house, like its size, the location, etc. And then the target value is the price of the house. I'm using here the apex equals to 256 and for the batch size 128. So we are loading the data, and the dataset we loaded it using scikit-learn because TensorFlow doesn't have this dataset. And we are using the function split, train test split, to split the data into training and test set, and I'm using 20% for the test set. And here we want to standardize the data, and I'm passing this argument axis equals 0. So I will get one dimension array of length d, the mean of each feature across all samples, which means that we are standardizing each variable individually. So each individual input variable, in this example we have 8 of them, will be standardized individually. Without this argument, you will get one single number, the average of all elements in the table, both columns combined. We don't need this. We need to have individual mean for each feature. And then we calculate the standardized training data and test data. And notice that I'm using the mean of the train set for both the training and the test. We always use the mean of the training data. Then we are creating the model here. We are using sequential API, and we have input layer with 32 neurons and using the activation function ReLU. And I'm mentioning here the input is 8 variables, and the second layer, which is the output layer, has 1 neuron with activation function linear. Remember that we are predicting one single value. And then we are doing the regression. And here the metric is using the loss function here, the mean squared error, because this is a regression problem, and we are using Adam optimizer. And to measure how accurate we are using mean absolute error. And here we are calling the model summary. In that way, we can print out the models before training the model. We can see the model before training it. So the total params is 321, trainable params 321, and non-trainable params 0. And as you can see, sequential. This is the output of the training data with 256 epochs, and you can see the loss here for the training data about 28%, and for the validation it's 0.29. Then to improve, then here we are, here we are now predicting the output using the model.predict, using the trained network, which we have implemented above. So we take the entire data set, which is the test data set, and use the model to predict. So predictions will give us the predictions of all of the examples, but I just want to print out the 3 of these predictions. Here we can see how close they are to each other, true value and the prediction. So let's see how we can modify this code to get better results. What I've did, I had added some more layers and also increased the size of the layer. So instead of using 32 neurons, I'm using here 256. And I added also another header layer and then the output layer. But when I ran it the first time, I saw that we got overfitting. In other words, I saw the training error was much lower than the test error. To mitigate overfitting, I added dropout regularization in between the two layers. And this is the summary of the model. And here, let's see the output. So after 256 epochs, it is a little bit slower when you do that because we have more layers, but it will be faster because it's a simple problem with a small data set. And we can see the loss function is better here because it was about 0.28 previously, but here it is better. So we have improved the network accuracy a little bit by making it a deeper network.